Hello students, welcome back to this online session on industrial metallurgy. In this particular session, we'll continue with the basic terms that are used in industrial metallurgy. And in this particular session, we'll talk about another important term, which is called equilibrium. These are the contents that we shall be discussing in this session. Now let us define and try to see as to what is meant by this term equilibrium. You see, equilibrium is defined as the situation or the condition under which the net resultant forces which are acting on any system, they are zero. And thus we can say that equilibrium is a condition when there are no unbalanced forces acting on the system. Specifically, if we talk in the field of industrial metallurgy, it is said that equilibrium is defined as the condition in which a materials system possesses minimum amount of free energy possible. Mind it, free energy is the amount of energy which a material possesses, so that under a given conditions of pressure and temperature, means under a given set of conditions, the system can bring about a change. The system can bring about a transformation. So if the system is not in equilibrium, it is not at its minimum possible level of free energy. And then when a system is present at a particular temperature and pressure, and if it is not possessing the minimum value of free energy under those conditions, conditions remaining the same, the system will have a tendency to transform and bring about changes in itself. So equilibrium is the condition of minimum free energy of the system. Then what's the significance of equilibrium? You see, when a system is in equilibrium, since there are no resultant unbalanced forces acting on the system will have no tendency to change with respect to time, however long that time period may be. And if a system is not in equilibrium, then it means that there are still some unbalanced forces which are acting on the system, and these unbalanced forces will keep on bringing about a change in the system, and this change will keep on happening until those unbalanced forces have reduced down to zero. That means the system has come down to equilibrium. Now if we talk in a physical sense, if we start considering our system as an object, then generally it is said that when a system is in a configuration where its potential energy is minimum, that configuration is called its most stable state or the equilibrium state. And if a material system is present in a situation, in a condition, in a configuration where its potential energy is maximum, then the system is present in its non-equilibrium configuration or most unstable state or unstable state or non-equilibrium state. And there can be infinite positions between these two states, the equilibrium configuration and the non-equilibrium configuration. One of the configurations between these two have been shown over here. So any configuration between these two configurations where the system is neither in equilibrium nor in non-equilibrium, any such intermediate configuration is called a metastable position, metastable state, or metastable configuration. Thank you. Okay, then what is the use of this term equilibrium in physical metallurgy or industrial metallurgy? Students, we will use this term in two different contexts. We will use this term equilibrium in order to do classification of the phases present in a material system, and we will also use equilibrium sometimes by referring to or by saying that the system is being cooled under equilibrium conditions, the material system is being heated under equilibrium conditions, and we must know that what do we mean by making this type of a statement. Okay, so when I say that we can classify the phases existing in a material system on the basis of equilibrium, on the basis of equilibrium, phases are of, see, there are several classifications how phases can be classified. Another classification that I'll discuss with you would be on the basis of the properties that the phases show. Here I am discussing with you that if we are talking in the context of equilibrium, then on the basis of equilibrium, what is the categorization of phases? Phases can be classified into three categories: equilibrium phase, non-equilibrium phase, and metastable phase. But you listen very carefully now. If a No, I'm trying to explain now that what is meant by equilibrium phase. If a phase is existing in a given material system under some given conditions of pressure and temperature, and this phase that is existing in the given material system under some given conditions of pressure and temperature, if these conditions of pressure and temperature remain the same, and this phase that is existing in the material system neither changes to any other form, to any other phase, nor has any urge or tendency to transform into any other phase, if these conditions remain the same, then this phase existing in this system is an equilibrium phase for this system. For example, if I say that in an iron carbon system, in a steel component or in a cast iron component, when it is at the room temperature, ferrite phase is existing. Now, if under room temperature conditions, ferrite phase exists in a steel component, and if you do not leave these room temperature conditions, 1 atmospheric pressure, 25 degrees centigrade, the ferrite phase that was existing in the steel component will continue to exist. How long, how much long time period may elapse if this condition of steel component of 25 degrees centigrade and 1 atm remains to be there, the ferrite phase also will also remain to be there. So ferrite phase for a steel component under room temperature and atmospheric pressure conditions is an equilibrium phase. Okay, then what is meant by non-equilibrium phase? If you look into a material system under some given conditions of pressure and temperature, and you say that under these conditions of temperature and pressure we saw a phase, we observed a phase, but sir, these conditions were maintained. With the passage of time, immediately this phase transformed to some other phase over an observable period of time, then this phase that existed in the material system for that small period of time is called a non-equilibrium phase. For example, if you look again into that the steel component under room temperature conditions, suppose you have quickly cooled down that steel component and brought it to room temperature conditions under rapid cooling conditions, austenite is a phase which might be seen for some fractions of a second, for some moments. But now these room conditions are maintained, but immediately under these room temperature conditions only, this austenite flame will quickly transform to some other phase like martensite or something else. So austenite phase for steel component under room temperature conditions is a non-equilibrium phase. Similarly, if you rapidly heat your steel component, which at room temperature was containing ferrite phase, under a high temperature condition, because of the rapid heating, for some period of time at a high temperature, say 1000 degrees centigrade, you might be able to see ferrite phase in the steel component, but within a short span of time at those high temperature conditions, ferrite will immediately transform to some other phase. So for the same steel component, for room temperature conditions, ferrite was an equilibrium phase, but for the same steel component at 1000 degrees centigrade, ferrite is a non-equilibrium phase. And students, third category, metastable phase. If for some given material system under some given conditions, some phase is existing, but under those conditions that phase is not transforming in front of you to some other phase, but it has got an urge or tendency under it to transform to some other phase, then that phase is a metastable phase. Say, because under some conditions, if a phase does not transform or even does not have a tendency to transform, then it is an equilibrium phase. But because this phase that I just spelled out is having a tendency, it's not an equilibrium phase. So is it a non-equilibrium phase? For non-equilibrium phase, under an observable period of time, say some minutes or say some hours, it must transform to you and give you some other phase. if even that is not happening, so this phase that we are discussing at the moment is not even a non-equilibrium phase. So it is put into a third category. So any phase existing in a material system, if it is not transforming immediately to some other phase, but at the same time it's not completely stable and has got an urge within itself to transform to some other phase under those given conditions, then the phase is a metastable phase. For example, there is a phase called cementite that exists in steel under room temperature conditions. Now if these room temperature conditions are maintained for suppose 1,000 years, this ferrite will transform into iron and graphite. But this change though is taking place, but it's taking place a very, very long period of time. So this is not a non-equilibrium phase, but because it has got an urge to transform and it does transform after 1,000 years, it's still not a equilibrium phase. It's a metastable phase. Then after having discussed that what is the type of phases on the basis of equilibrium, there is another way how we use equilibrium, that we are doing equilibrium heating or cooling of a material system. Students, whenever somebody says that a material system is being heated or cooled under equilibrium conditions, it means that the system is being heated or cooled at an infinitesimally slow rate. The system, if it is being heated under equilibrium conditions, is being heated at a very, very slow heating rate. If it's being cooled at a equilibrium cooling rate, means it's being cooled at an infinitesimally very, very slow cooling rate. Why? So that during the course of heating, because the rates of heating are so slow, whatsoever processes want to happen in the system at the intermediate temperatures that are coming across during heating or during cooling, those processes get sufficient of time to get complete, so that when the resultant system comes at its final state after heating or cooling, that is under complete equilibrium. So when a system, whatsoever we have written, and what would be the effect of equilibrium heating or non-equilibrium heating? See, if a system has been heated under equilibrium conditions, when the system comes after heating or cooling to its final state, such a system is completely stable, does not have any unbalanced residual forces in it. So the system will have no tendency to change with respect to time. Also, the system will be completely chemically homogeneous throughout its cross section. And if you do not do equilibrium heating, then all these ill effects like non-uniform composition, development of some residual stresses or unbalanced forces would be seen in a system. Thank you for watching.